Yeah, hello. Hello. Hello, class.
Hello, sir.
Good afternoon.
Hello, sir. Good afternoon, sir.
Good. I
Good
hope
afternoon, sir.
I hope you are doing well.
Yes, sir, you're doing well. By God's grace. Hope you are doing well too.
Yeah, I'm also doing well. Mhm. Okay,
Thank God.
so let's begin the class. So this question should have helped us to wrap up on kinematics in two dimension as well as on frictional force. Okay, yeah, assumptions of frictional force in what in place. Good. So today we are starting with something else. We are looking at the work energy theory, but aside that, we will briefly look at some theories on the gravitational motion. Okay, then after that, we'll look at the work energy theory, solve some few examples, and also look at moment conservation of energy. Okay, and then if we have enough time, we can look at circular motion, which is a brief or connects to what rotational motions. Okay, so gravitational motion. So what we are saying is we've looked at a number of motions so far, okay, around us, seeing how the kinematic equations apply and all that. But all those were based on, uh, I mean, we assume that we're looking at this motion on Earth. These are motion of particles, okay, on Earth, and how we're able to estimate or to predict their trajectory, okay. Now we have other bodies in space, and there are laws which also govern their motion. So there are some few laws we're going to look at. The first one relates to the Newton's law of universal gravitation, okay, which states first of all that every mass in the universe attracts another mass with a gravitational force, okay, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, yeah, so basically what we are saying is the force of attraction between the earth, the moon, or the earth and the sun, okay, is what that force of attraction between, let's say, the earth and the moon, okay, or even two bodies, let me put it that way, okay, is just directly proportional to what the product of their masses. So that will be the mass of the earth, okay, times the mass of the moon, okay, and inversely proportional to the square of the distance between the earth and the moon, okay, which also means that we can rewrite this mathematically, bringing the constant of what, okay, bringing the constant as f is equals to, so we can write this as f equals to what, g, okay, m1 m2, okay, over r squared, okay, where g is a constant of what, gravity or gravitational constant, the universal gravitational constant, okay, and the value of the universal gravitational constant is indicated, okay, here, so we take note of that. Okay, now this can be used to find some few, to solve some few questions, given what, if we are given the mass of the two bodies and then we are given the distance or the radius between them, okay, then given a constant what, universal gravitational value, we can easily find the force of attraction between the two bodies. Okay, now moving on. Yeah, so that is Kepler's law. There are laws which Kepler also proposed, okay, regarding objects, okay, the motion of objects in space. Okay, the first one has to do with the law of orbit, the law of area, and the law of period. So we are briefly going to look at these laws. Okay, the first law says that all objects move in elliptical objects with the sun, okay, at one focus. So here we are referring to what? Our galaxy, okay? We're referring to our galaxy. So we have the sun, okay, and all other objects move what? In elliptical paths, okay, around the sun, okay? So we have all other objects in our Milky Way, okay, move in elliptical path. That is what Kepler says. The second law, which is also demonstrated in the next slide, says that the line joining the planet and the sun sweeps through equal area, okay, in equal time, okay. So we'll look at that in the next slide. Let me just move to that. So we are saying that, okay, the line, so this is the demonstration of the first laws. Okay, so we can see that all the objects are moving around the sun in elliptical what? In elliptical paths. Okay, that's for the first law. And we are saying that the line joining the planet and the sun sweeps through equal areas in equal what? Time. Okay, so given the same time, okay, the area that is going to sweep through, okay, within this time here, will be the same area within this time here. So it's indicated that we have equal area in what? In equal time. Then so there's a demonstration here, the law of equal areas. Okay, very good. Now finally, the third law says what? That the square of the period, okay, of any planet, that's the time it takes for revolution, is proportional to the cube of the semi-major axis of its orbit, where m is the mass of the planet. So we can see from the formula here that the square t of the period t is equals to 4 mu squared over what? G times the mass, or times what? R cube. Okay, so these are laws we just have to know. Okay, we'll not be solving much questions on them, will not dwell much on it, but these are laws you have to know, that with bodies that are in space, there are other laws which govern them, like the Kepler's laws and then the Newton's gravitational law. Okay. Yeah. So today, our main focus is to look at work energy theory. Okay, and a part of what we'll be looking at, we'll be looking at momentum, we'll be looking at energy, we'll be looking at what work is, we'll be looking at kinetic energy, potential energy, and how to break all these parameters, okay, down for estimation. Okay. Now, the first thing we are looking at is momentum and impulse. Okay, so the question is, what then is momentum? Momentum is just the ability of a body in motion. Okay, so we can define it as the mass times the velocity of what? The body. And from, okay, these laws here, as we are seeing, from the law of impulse, we can re-express, okay, we can re-express the linear momentum in terms of this equation. So impulse is also defined as force times the change in time here. Let me change my marker. Impulse is defined as force times the change of time. Okay, and momentum is mass times what? The velocity. Okay, So if we can rewrite the impulse at the time of impact, okay, is equals to the momentum of the body, then we can also re-express, it can be proved that the force applied is equals to the rate of change of what? Momentum, okay? Which was the initial law that Newton was proposed, okay, that the force is equals to rate of change of momentum before it was revised to what? The net force acting on the system causes an acceleration of the system. Okay, so we take note of that rho is equals to what? mv. Okay, that's a key note we should take from here. Yeah, so what next? The next thing we have here is the principle of the conservation of momentum, which states that if there is no external force acting on a system, then total momentum on the system remains what? Constant. Okay. Or we can also state that when there are no external forces acting on a system of interacting particles, the total linear momentum of the system remains constant. So in other words, momentum is not lost, okay? The total momentum before an impact is always equals to the total momentum after the impact of what? A system of interacting what? Particles. Okay. So there are two main types of collisions. Okay, when two bodies interact, they collide. And the two main forms of collision we can have are the elastic and the inelastic what? Collision. When we talk about elastic collision, we are talking about a collision where two objects, okay, or let me put it, the kinetic energy of the objects interacting is conserved, or the object which would collide is what? Conserved. So for example, you have let's say two ball, okay, when you knock the balls at each other, you realize that they will come back, okay, in the opposite direction with the same what? uh, Energy. So the kinetic energy is what? Conserved. Just that to a point, some amount of the energy is lost through what? Sound and heat. Then we also have what we call as inelastic collision, okay, where there are immense, okay, losses of kinetic energy due to frictional losses or deformation of what? Objects. Okay, so when two cars hit each other, okay, we have an inelastic collision because the objects will begin to deform, they crash. So there is deformation. And the initial momentum, that ability for them to move, okay, is transformed into deformational, let's say stress, okay, is transformed into stress, which causes deformation or a strain in the various what? Objects, okay. So our kinetic energy is lost due to our frictional losses and deformation of what? Objects. Okay, so we are getting close to solving some examples on this. The first one is we are looking at type 1 collision where two bodies, okay, coming from opposite direction stick together afterward, after collision. So in other words, we have these two bodies like this. Okay, this is before momentum. This is before momentum. Okay, and then after momentum, you have the two objects. Okay, you have these two balls. Okay, the blue ball and the yellow ball moving together. Okay, with a common velocity. We can't tell exactly where it is until we solve, okay, whether we are coming here or we are coming there will depend on the momentum each object had from before the collision. So as a word problem, we have a 90 kg fullback attempts to dive over a goal line, okay, with a velocity of 6 meters per second. Okay, and to illustrate this, let me just go to the diagram. Then we come back to the question. So this is what is happening. Okay, probably. Yeah, so this is what is happening. We have the fullback, okay, the 90 kg fullback trying to go across the goal line. Okay, and then once he goes across this line here, then it means that he has scored what? A goal. Okay, but this fullback is also the linebacker, okay, is trying to prevent him. So which means that he's going to hold on to this player here, okay, and hoping that his momentum, okay, will be able to move, first of all, stop the momentum of this fullback here, okay, so that the two of them will move in the same direction. That is the intent, okay, but as to whether indeed they will move in the same direction or not is another matter, which depends on their momentum, like we said. So let's go back to the question and read it carefully. So we're saying that a 90 kg fullback attempts to dive over the goal line with a velocity of 6 meters. He is met at the goal line by a 110 kg linebacker moving with 4 meters per second in the opposite direction. The linebacker holds on to the fullback. Does the fullback cross the goal line? Okay, so let's go back and do the analysis. So we've been given their velocity, we've been given their mass, and then we are asked to find what direction, okay, the two bodies, okay, will move after collision. So like we said, then the initial, the principle of conservation of momentum, okay, then the momentum before, okay, is equal to what? Momentum after, right? And then clearly we can see momentum before when the two objects were coming, okay, we have the momentum of object one, okay, and the momentum of object two, okay. Then for final, so this is before, then this is what? Afterward collision, okay, good. So after the two of them will move together, so it means that their mass will be the M, capital M, okay, will be small m1 plus what? Plus m2, okay, m1 plus m2. Okay, so let's see how this will be calculated. Now again, we'll need to take into consideration the direction, okay, because velocity is a vector quantity, okay. So we need to take into consideration the direction of the two the two objects. Let me put it that way. So for the fullback is moving towards our what? Negative x, okay, and then linebacker is moving what? To the positive x, okay. There are other ways of looking at this though, but I think we are being consistent toward our initial proposal of using our coordinate system to demonstrate the direction. Okay, so we have negative for, so if m1 here is for the linebacker, if m1, okay, so m1 is rather this fullback here, and then m2 is the linebacker. Okay, so from this equation here we can find the final velocity by just dividing through by the mass of the object, okay, which is basically m1 times the velocity v1, okay, plus what? We have m2 times the velocity v2, okay, all over what? All over, and these are all initial velocities, okay, all over what? All over m1 plus what? Plus m2, okay, good. So having said that, we'll substitute the given values. M1 is 90 kg. This is the mass. V1 is what? Is 6 meters, but because we said we are moving in the negative, we have negative 6 meters per second, plus the mass of 2 is 110 kg, okay, times the velocity, which is 4, okay, 4 meters positive, so positive here, over 90 plus what? 110 kg, okay? And then once we do this calculation, you can check it from your end. Use your calculators to check from your end and give me your final answer. If there is any question you can ask, before I move to the next class.
Sir,
Yes.
I have a question.
Yeah, go ahead.
Okay. So when you look at the player with the 90 kilograms,
Yeah.
and that of the other player with 110 kilograms,
Yeah.
you realize that by nature,
Yeah.
the 110 kilogram player will be stronger than the 90 kilogram player. But finally, we realize that the 90 kilogram push the other player down. What necessitates that?
Okay. It's the momentum. You see, the 90 kilogram and the 110 kilogram, they are all heavy. The main difference there is the 90 guy is moving very fast. He's moving far faster than the 110 kilogram.
Okay.
He's moving quite quicker.
And that is the momentum.
Like I told you, the basic definition of momentum is the ability of the body in motion.
Yes, sir.
So the speed with which the object moves also counts a lot. Okay. Yeah. Okay, so let's move. Yeah, we have the second case. Okay, we have the second case where two bodies which initially, okay, came together will split up. Or yeah, two bodies initially together will split up, okay, after collision or after interaction. Okay, that is a gun scenario or a rocket scenario, okay? Before a rocket will take off, you can see that a set amount of gas and fire, okay, which is equivalent or which is enough to just raise the rocket in the other direction, okay? Or for the gun and the bullet scenario, when you shoot it, the bullet moves, they were together, okay, with a common velocity. Then once you shot it, the bullet moves in one direction, the gun moves in the opposite direction, okay? So this is case type 2. And we've been given a question here. It says, the bullets of mass 0.02 is fired by a gun of mass 100 kg. If the nozzle speed is the speed of the bullets, okay? That's what happens at the tip of the gun. So the nozzle speed of the gun is 80 meters per second, what is the recoil speed of the gun? Okay, what speed does the gun move backward? We call it the recoil speed. Okay, so we've taken note of that. Mass for the bullet is what, 0.02. Mass of the gun is 100 kg. Then the velocity of the bullet, okay, is what is, or the bullet, small m, okay, is 80 meters per second. And the two bodies are moving apart, okay? And we've been asked to find the velocity of what? Of the gun. The recoil speed of the gun, okay? Good. So what we do here is you consider the direction. Initially, yeah, so if we let V be the recoil speed of the gun, then per the conservation of linear momentum, we have initial momentum is equals to final momentum. But we know that because the gun and the bullet were together and they were not moving, then it means that, so ideally it would have been, because they were together, their mass will be m plus what? Small m, okay, times velocity, okay, but the velocity is equal to 0. And then equals to, now their new motion will be what? mv plus what? M, okay, v. You understand? So this is how it looks like. Very good. So now we know that because this is 0, it will come down to this equation here. Okay, good. Then again, yeah. So which tells us that we can rewrite this equation in this form, that the velocity is equals to the minus of mv over what? Over m. Okay, which is going to be the mv, m is 0.02, the velocity of the gun, the bullet is 0.80, and then the mass of the gun is 100. So we are going to get negative what? 0.016. Okay, so what is happening here is, because we do not know which direction who is going, okay, if you make this plus, if we consider this to be plus, okay, I've seen 2 hands raised, just be patient. If we consider this to be plus,